Well, hello there. I think we need to talk about bonding. There's so many different bonding models that we learn, and we usually start out talking about just ionic versus covalent bonding. And then, if we go into covalent bonding, we draw out Lewis dot structures. And then, once we've drawn out our Lewis dot structures, we can begin to look at shapes, molecular geometry. Like, why does this atom here have this tetrahedral shape with the atoms that it's bonded to? We learn about that with Vesper theory, valence shell electron pair repulsion theory. My dog is coming over. Can you hear his little footprints? He's wondering why I'm talking. Why I'm talking. He thinks I'm talking to him. This little snout. I'm gonna move the camera a little bit so you can see him. Oh, now he's gonna go away. Well, he's very cute. I'll have to show another video of him. He's a corgi. Yeah. Okay. So anyway, as I was saying, we have the Vesper model. He's so funny. He jumped up on my lap here. Or he tried to. His legs are so stubby, he has a hard time. So, we have the Vesper model that helps us determine bond angles and things like that. And then we have valence bond theory, which talks about hybridization and gets a little bit more theoretical. Brings in quantum mechanics, brings in computations. But it is consistent with what we see with Vesper, with the bond angles. And so far with Lewis dot structures, with Vesper, with hybridization, all of those bonding models are consistent with one another, and they make predictions that are pretty reasonable. Nothing's too surprising. But this is the problem. They cannot predict certain things like, why does, when you hit a bond, hit a molecule with a certain amount of energy, like with a photon, what causes it to break that bond and have that break apart? So that's something that these bonding models we just talked about, they can't really predict. Also, there are some molecules that have unpaired electrons that we would not expect with Lewis dot or any of those other bonding models. And that's where molecular orbital theory comes in. And I have made videos before talking about molecular orbital theory, but I really wanted to approach it today from an introductory standpoint and really talking about the fundamentals of this really important and helpful theory. So with molecular orbital theory, the difference now is that the orbitals aren't seen as orbitals that belong to each individual atom. Oh, that's funny. I put S there. It's molecular orbital theory. I think I was saying orbitals. Okay. So the approach of this is not that there are individual orbitals that belong to each atom that then come together and overlap with this kind of separateness. Molecular orbital theory sees the orbitals as belonging to the entire molecule. All right, so that's where we will be heading. And we're going to use our example. It's always good, and I always do this, to start with the simplest molecule that we can. And that would, of course, be H2, hydrogen. Okay, so when we consider the hydrogen molecule, not so surprisingly, we look at two hydrogen atoms and their original atomic orbitals, the 1s orbitals in this case. Okay, so here's one hydrogen, and here's the other. Okay, so we'll just look at these separate from one another. And their atomic orbitals, they each have one electron. And then what we are going to do is now consider overlapping them. Okay, so we're going to bring these two 1s orbitals together from each of these hydrogens. Okay, and so we're thinking, all right, let's make this H2. But let's go beyond what we would just say if we overlap them and make H2 molecule. This, I would say, is more of like the other bonding models we've looked at. Lewis Dodd or Vesper or anything else. Okay. What molecular orbital theory does is it uses a mathematical technique, we might call it, called linear combination. And that's something from linear algebra. If you've taken linear algebra, matrix algebra, you've done it. But if you haven't, that's okay, because we're going to go through what this approach is and how it's consistent with what we know already about electrons, which behave as waves. So if we go back to when we first learn about quantum mechanics, and one of the things we learned is the wave-particle duality of electrons. And so because electrons behave as waves, that means that they can undergo constructive interference. Let me just remind you what that is. Constructive. Do a little side note here. Interference. If we look at a wave, okay, that looks like that. And then we imagine another wave where it is coherent with that wave. When we add these together with constructive interference, we get a larger amplitude. Okay? These bolster each other with the amplitude, as opposed to destructive interference. Whoa, interference. That would be where you have a wave, and then the other wave is essentially the opposite of coherent. It's completely incoherent, where the peaks of one wave are lined up with the troughs of the other. The net result of this is flat line, zero amplitude. So this is just general wave behavior. But if we think of this in terms of electrons as waves, this corresponds to there being a high probability of finding an electron, whereas this corresponds to zero probability of finding an electron. Okay, so this is our reminder of wave behavior. And now let's apply this to if we look at this area here, this overlapped area, and if we now look at this as constructive interference, or in other words, we're adding, so I'll put constructive, okay, so this is additive of that overlap, or in other words, this is going on. That means that this area where we can find an electron gets larger, just like we saw here. And so, this resulting orbital is now larger in between the two nuclei. So let me actually go back and draw in the nuclei, which I did not do before. Okay, for each of these hydrogen atoms that we started with. Because ultimately now we have this molecule with the two nuclei. And see how this area between the two nuclei, there is now a much larger probability of finding an electron between them by virtue of adding together that overlapped area. So notice how we have a lot of electron density that's possible between the nuclei. What kind of bond is that? Is that a sigma bond or a pi bond? And if you were thinking sigma, you are correct. And so, this is called a sigma molecular orbital. And in this case, by virtue of this molecular orbital being created, by adding together the overlap between, this is a bonding molecular orbital. Okay, and this is more stable than two individual 1s orbitals. Okay, from those two H atoms. So the way I drew this here is actually also showing you energetically that these two are higher energy than this resulting molecular orbital. So I did that on purpose, actually. Okay, so now let's look at if we carry out destructive interference, or in other words, if we subtract one of these orbitals from another, you could say, in between the two nuclei. Okay, so that's kind of like what we talked about here. Subtracting the wave amplitude and getting this flat line, or in other words, a node. So now we have our two nuclei. Okay, we have created a node. 0 probability of finding an electron between the two nuclei in this region. Now, there's still electron density, there's still probability of finding an electron on the outside, but we have subtracted away a lot of this region in between. So the resulting molecular orbital for destructive interference is called an antibonding sigma orbital. And antibonding is denoted by the star or the asterisk. Okay, this is antibonding. And what we have done here is we have created a situation where there is destabilization. Think of these electrons here. They do not have an opportunity to maximize their association with this positive charge in terms of electrostatics, the negative electron and the positive nucleus. Over here, the electron has equal opportunity essentially all around the spherical region around the nucleus. But here we have this asymmetry, and this ends up being less stable than what it would have been. So antibonding orbitals, these are less stable. Less stable than the two original atoms, and definitely much less stable than the bonding molecular orbital. Okay, so I'm just going to say this is less stable. Okay, come on. Something's up with my ink. Okay. Less stable. And that is always going to be true for our antibonding molecular orbitals. They will consistently always be less stable than the original atoms and the bonding counterparts that are here. Another thing I want to point out is that this is always true. However many atomic orbitals you're beginning with, that is equal to the number of molecular orbitals you end up with. So you can think of this as a kind of conservation of mass. 2 atomic orbitals go in, and 2 molecular orbitals result from this. So this is the fundamental basis for molecular orbital theory. This is the approach. There's always an overlap of orbitals, the atomic orbitals, and then there's a constructive interference, and there's the destructive interference that results in a bonding molecular orbital and an anti-bonding molecular orbital. We can also show this energetically with what are called molecular orbital diagrams. And what's interesting about this, they're called MO diagrams. But the word energy is always left out, and I don't know why that is. But it is inferred. Okay, so always think of this as an energy diagram. And they look like this. Okay, there's convention to MO diagrams. So first off, it's always energy diagram, where stable is down here, less stable is up here, lower energy down here. And the convention is to have the 2 atoms that you're concerned with, because we will only ever be looking at diatomics, 2 atoms in the molecule, beyond that, it gets more complicated when we're first starting out. So we always start out with just diatomics, like H2. So the convention is we list the atomic orbitals for each atom on the outside, flanking the molecular orbitals, which are then in the center that result. And because this is an energy diagram, similar to when we're drawing these energy diagrams for atomic orbitals, we have whatever that energy is, and we actually, oftentimes, especially when we're starting out learning about molecular orbital theory, we don't even worry about exactly what that energy is. We are more concerned with the relative energies. These two, same atom, same orbital, so they will have the same energy. The molecular orbitals, on the other hand, as we discussed above, the bonding sigma, lower in energy, more stable. Antibonding, higher in energy, less stable. One thing that you'll see often in textbooks, these little dashed lines. They are not necessary, but they're commonly shown. And the reason why they're often shown is to just depict which were the atomic orbitals that were combined to give the molecular orbitals that resulted. And with H2, it's fairly simple that it would be the 1s orbitals that would come together. But with bigger molecules, it gets more complex. And those dashed lines can actually be helpful to include. So, the main thing is that we have these atomic orbitals here and here, and we have the molecular orbitals here in the center. And then we put in our electrons. So this is where we acknowledge hydrogen atom has 1. This hydrogen atom has 1 electron. And now we take those electrons from the atoms and we dump them in. We don't worry that these are spin up. We're just worried about how many there are. And we put them into the molecule following the rules that we have learned from any of our orbital filling diagrams. One of those rules is the Aufbau principle. The Aufbau principle says that you always fill the lower energy orbitals first. Aufbau, from German, building up. So you put those electrons into the lowest energy orbital. Alright, so here is our MO diagram for H2. There's one other thing we can do with this. And we can calculate bond order, which tells us the strength of the bond. And we can acknowledge that bonding molecular orbitals are more stable, and they are going to contribute to a stronger bond. And so when we calculate bond order, we'll call it BU. The number of electrons that are in the bonding molecular orbitals, those are going to contribute to a stronger bond, to stabilization. Meanwhile, if there are any electrons in antibonding orbitals, those are going to destabilize the molecule and they're going to weaken the bond. So we subtract out any electrons that are in antibonding orbitals. Okay, now, because for each bond there are 2 electrons, we need to divide this by 2. So in the case of H2, we see that there are 2 electrons in the bonding molecular orbital. There are 0 in the antibonding. Divide by 2. And that gives us 1. Or in other words, we have a single bond. And this is consistent with if we were to go back in any of our earlier theories like Lewis dot. This is a single bond. It's consistent. And that is good. That is what we need. Molecular orbital theory gives us additional information. It's not a theory that gives us anything that would go against what's already known. And this single bond, the strength of this bond, that's consistent with experiments where they've studied the strength of the bond. It's consistent with it being a single bond. So experiment, Lewis dot, molecular orbital theory, all these are consistent with each other. They just have different strengths, and we get different pieces of information from each of those theories. All right, well, I hope that if molecular orbital theory is somewhat of an enigma to you, that I have alleviated a little bit of that mystery and given you some insight into some of the fundamentals of this very important, somewhat sophisticated bonding theory. Thank you so much for being here with me. Please subscribe and don't ever hesitate to share this channel with other people who are studying chemistry or enjoy chemistry, or maybe you just enjoy hearing about science or chemistry in the ASMR style. Either way, I am here for all of you, and I will continue to make these videos. I promise you that. So have a lovely day, and I will see you again next time.